So welcome back, everybody, to another webinar organized by Princeton University's Bendheim Center for Finance. We're very happy to have Esteban Rossi-Hansberg with us. Hi, Esteban.
Hello.
So Esteban will talk about the economic geography of climate change today. So we are broadening our theme a little bit beyond COVID, like we did last time. And before we go to Esteban, some housekeeping and some introductory remarks on my side. As I mentioned, Jean Tirole was actually here last week talking about the public and private sphere and the authentic self. So that's something to watch on YouTube. Today we talk about climate change, and we had an earlier climate change talk by Richard Zeckhauser, who was talking mostly on geoengineering and making a case that we should do some geoengineering. Then we have coming up Chris Sims, Bengt Holmström, and later on Esther Duflo. We have to reschedule Esther. She will come actually later on. So let's start with some introductory remarks on climate change. As we said earlier, there are two approaches. One is a Malthusian approach, where we essentially have to cut back on consumption, cut back on all the achievements society has achieved to a large extent. Or we can have an innovation approach, where we really try to innovate and do new things. And innovation can come in three forms. We can innovate to mitigate and reduce pollution. We can adapt. We can build some dams, seawalls, and do migration, and Esteban will talk about that as well. Or we can do some amelioration, like geoengineering that Richard Zeckhauser was talking about. So these are three different ways you can move forward. And the question is which way we should put the most emphasis on it. And all of this is a big long-run project, so it's a dynamic effect. So we talk about 100 years. So Esteban will present a model which looks, I think, more than 100 years into the future. So there's a lot of uncertainty involved. And I think for studying uncertainty in such an environment, the main driver is mean reversion. So what's, is the system coming back? Is it stabilizing or is it destabilizing? And actually what's really important is also for innovators is to have essentially some planning certainty. So you reduce the uncertainty. And I would like to talk a little bit about the uncertainty components and how important it is if you impose a carbon tax, then actually you have a whole path. Don't introduce additional uncertainty with the policy aspects. So in terms of uncertainty and risk, you can think of three different ways uncertainty and risk is showing up. One is that the climate change itself is volatile. So the climate volatility, it's very hard to predict. We have climate models, but there is just some prediction. There's a lot of uncertainty around it. Then there's some uncertainty how big the damage function will be. So if there's climate change, how much will it damage the whole environment? How much will it damage our livelihood and so forth? And then there's uncertainty how the policy will play out and how the politicians and how our policy, how will it respond to that? And all these different uncertainties make essentially the whole predictions much more complicated. And it also makes the remaining consumption we have more volatile as well. So these uncertainties actually call for more weight on the future. That's essentially a very important insight we talked about last time already when Richard Zeckhauser was here, where it's actually the case the discount rate you put on here, this little r, depends on the time reference rate. So how much you discount future utilities compared to current utilities. Then you have this expected growth rate. If future generations are much more wealthy than we are, we don't actually discount more and hope that future generations will actually do it because they're much more wealthy than we are. But the uncertainty essentially, if there's more consumption growth uncertainty going on, the discount rate is lower. There's a minus sign here. And then of course, if we do some investments today, then actually also reduces the downside risk of the remaining consumption growth. And that's also helping. So that brings the discount rate down too. A low discount rate means you put a lot of weight on future periods. And that's actually means, you have to do more action now rather than postponing it. But the key, as I mentioned before, is that in the long run, the variance of the growth rate depends a lot on the mean reversion. So mean reversion is one very important factor to understand. And if you have a system which has tipping points, and if you go beyond a tipping point, it just goes way out there, then you don't have much mean reversion. It's exactly the opposite of mean reversion. So in order to focus on, the discounting, when you should do it, how should you ramp it up. The mean reversion component is very important. The second aspect is that you would like to have a policy which is responsive. As uncertainty unfolds, you would like to respond to it. So you would like to have a policy, if this happens, then we will do that in order to minimize risk. And you want to do this in a way that the risk is not offloaded to the innovators or the early adopters. Because if the early adopters have a sense that there will be risk offloaded whenever let's suppose they adopt the things and then it doesn't turn out so serious, then there suddenly be all the risk, they wouldn't make the first steps now. So that's very, very important for policy design as well. Now, Esteban will also talk about migration. How can we adopt if we have migration? So what I did is I looked at the globe and looked at the population density. And what you can see in this population density, so there is not much population density in some, deserts here in the Amazon, and then there's desert areas here and here. But there is, in all the cold areas in Siberia, in Russia, as well in Canada, there's probably a lot of new space opening up. The question is, what is the room for, is there some positive benefits from climate change, not only negative benefits? And what you see, the high population densities you have here in Asia, in particular Bangladesh, and also in China, which are very hot areas, so to climate change, they might suffer the most. And the question is, to what extent can innovation and also migration help here? And they have three cautionary remarks. One is migration probably leads to political conflicts. There are different ways to approach this. You can have what I call the Canada approach. You have to welcome immigrants. You say, okay, there's new areas opening up. We welcome immigrants. We build our GDP is going up, and we enhance our influence in the global community, and also the existing inhabitants, citizens benefit from that. And for Canada, it's probably a big change. The same is true for Russia. And the question is, what will Russia do in this sense if things are opening up? Will they say, okay, we will have new big cities developing in Siberia or something, welcoming immigrants or not? It's just some random thought here throwing out. The second thing is, once you have migration, will it be a migration that everybody's actually shifting up a little bit to the north? Or will it be that the people which are mostly hit with the climate change will actually jump over the people in the middle and move up much north? So is everybody shifting in parallel? Everybody is shifting up. A lot of migration in a sense that people coming from the south, making real estate prices more expensive and essentially driving the next layer up? Or will it be the case that you actually jump people which are displaced because of the climate change? They will move and jump to the areas which are much more up north. And the question is, what is socially optimal in terms of moving, and what is individually optimal? And this, of course, depends very much on some moving fixed cost. And it's interesting to see whether there are some geographic aspects to it. And Esteban's focus is very much on the geographic perspective to that. The other aspect, the third point I would like to make with regard to migration, is this climate volatility. So if, for example, climate change leads to more volatility rather than a parallel shift that all areas become more warm and then we can adjust through migration. But if everything is more volatile and there are more storms, and at short notice suddenly there's a new storm coming up and you can't escape the storm, so you can't relocate every 2 weeks in another location if the volatility is very high. So rather than having a calm climate as we have mostly now, or we had most now, we have much more volatile climate. Migration is actually not a good device to overcome climate volatility. So let me conclude with two types of innovation and a diabolic loop about that. So essentially, one hope is that innovation will actually help us to reduce emissions, and that's very, very good innovation. But there might be other innovations which might help us to better cope with a different climate. So we have an innovation, everything gets more warm, and then we have a much better air conditioning system, let's say. But I want to warn that this second form of innovation might come what I call this air conditioning diabolic loop. So I talked earlier about, with Raj Chetty's webinar, about the Roomba effect. Now I talk about the air conditioning diabolic loop. Essentially, the idea is, we have a hotter climate, then people adopt to that, they get more air conditioning. This needs more energy, so you have more energy here. That the more energy leads to more pollution, then we get even a worse climate, and so you have this diabolic loop. So one has to watch out, not any innovation is good. So innovation which reduces emissions is actually very much helping, but innovation which actually is just helping us to cope with the climate change and actually causes some negative side effects might actually be counterproductive. So one has to watch out for this innovation. The question is, which type of innovation will be more likely to come? Which type of innovation will the unregulated market economy pick? And is this a market failure or not? Let me conclude as usual with the poll we asked you. And the poll was proposed by Esteban. So what are the main mechanisms economies have to adapt to climate change? And we gave 3 options. One is technological innovation, mobility, migration, or international trade. And you said 84% said, it should be technological innovation, or it's most likely technological innovation. Mobility is only 10%, and trade was about 6%. So everybody is hoping on the technological innovation. We will see what Esteban's perspective is on this and what this model delivers for us on this perspective. Now, the second thing, what's the best policy to combat climate change? Is it carbon taxes, clean energy subsidies, or emission restrictions? Most people think, 65% people think taxes, carbon taxes will be the best policies. I should also have specified, how likely is it that it will come? Probably, there's a lot of resistance against carbon taxes. Clean energy subsidies, only 15%, and emission restrictions are 20%. Okay, so emissions restrictions are more popular than energy subsidies. And finally, do you think there is some international transfer necessary to help poorer countries to cope with the climate change? And the overarching majority, 87% think yes, and 13% thought no. So that's, for me, I pass on the floor or the screen to Esteban, who will outline his vision and his model, how to deal with climate change. The floor is yours, Esteban. Thanks a lot for being with us.
Thank you, Markus. So today, so thanks very much for having me. It's great to be able to talk about this topic. Let me mention briefly that everything I'm gonna say today is joint work with José-Luis Cruz, who is a great student here at Princeton. And so, like Markus said, when we think about climate change in general and global warming in particular, which is going to be my focus today, we're thinking about a phenomenon that happens over very long periods of time. So it's a very protracted phenomenon. And it is global. So what one particular region does affects the whole world and affects global temperatures. And so it's a classic case of an externality in which we all kind of affect each other. And so these particular characteristics have have influence in some sense the way we understand this phenomenon. And there's another key characteristic which I want to highlight today, which is that those effects of the larger temperatures are also going to have or have already very heterogeneous local effects. And by that, and you can understand that in different ways, but one particular way in which to understand it is that, that those increases in global temperatures actually lead to changes in local temperatures that are very different across locations. And then on top of that, those changes in local temperatures have very different economic effects depending on the characteristics of the location and also like the baseline temperature of that location. And so, when we think about assessing these phenomenon, building models to understand it and to try out policy and design better policies, as Markus was discussing, to deal with it, to adapt better to it, to maybe respond to it and ameliorate it, we need to think about these special characteristics of this phenomenon. And they should be at the center of our, at the core of our thinking about it. Now, when you look at the standard models that we have, you know, to think about climate change, and of course there's been lots of progress there with the work of Nordhaus and many others, Greenstone, etc. You know, there's great progress, but I would argue that that analysis, those models in general, miss two key components. The first component is that they normally rely or usually rely on loss functions. And by that I mean, like, these are relationships between output for the world as a whole or for very large regions as a function of temperature. And so they essentially postulate the loss function, maybe estimate that loss function with some available evidence, but that loss function is kind of fixed. And so it doesn't include, you know, it's not micro-founded, it's not in general, and as such does not introduce or does not include behavioral responses. So modern economics, of course, it's all about introducing those behavioral responses. It's all about modeling the firms, modeling the agents, and aggregating from that. And that's important because, of course, when things change, when we apply policy, etc., those aggregate relationships that maybe held before may not hold anymore, you know, in the future once those phenomena happen or those policies are put in place. So that's not, you know, normally understood as the Lucas critique. And so we want to kind of model those behavioral responses and that way incorporate, you know, economic adaptation in different forms. So that's going to be kind of one of the cores of what I'm going to talk about. The other one is that, as I said, there's vast spatial heterogeneity in these climate damages. And so we want models that have that, you know, spatial detail, and in particular, the relationships between these different locations. And how do these different locations interact with each other? Well, they interact through trade links. Of course, they trade goods, but they also, you know, people move across them. And so we want to bring those links or those spatial links between locations into our analysis and allow them to react to the effect of climate, but also for, you know, changes or movements in those margins to affect climate itself. And so that's kind of what kind of the agenda that I want to talk about today is essentially trying to build dynamic assessment models with spatial details that incorporates this type of economic adaptation through migration, trade, and innovation. Okay, so I'm not really going to go through the details of these models and all the different kind of equations that form them, etc., because we don't have time here. Maybe it's not the point of this talk. But let me just give you kind of a little sense of what type of structure we're gonna use or I'm gonna use in order to produce the results that I'm gonna show you in a minute. So the core of this is these quantitative spatial models that, you know, the literature in trade and spatial economics has been developing for the last couple of decades, and that by now are, you know, fairly useful models to and can be matched to the data in a very kind of effective way. And in some previous work with Klaus Desmet and David Nagy, what we've done is, you know, develop these models, kind of dynamic versions of these models where there's growth and there's a kind of investment that can lead, or investment in technology that can lead to growth. And so that generates like spatial growth models in which the distribution of economic activity where people are determines, you know, the incentives of firms to innovate and improve local technologies. And so these are models in which the distribution of economic activity affects growth, and then growth itself also affects the distribution of economic activity. And so, you know, the economy evolves over time as a result of, you know, how people move across space, how people trade across space. And so they incorporate costly trade and costly migration. Okay, so that's the core of the economic model that we're gonna use for this. And this kind of, you can see that, you know, in like in the diagram that I have on the screen. And then what we're gonna do in order to incorporate, you know, this climate change and incorporate fossil fuels is to first, you know, add energy as one of the inputs in production. And there's going to be two types of energy. There's going to be clean energy and fossil fuels. And then fossil fuels, of course, are going to emit or generate CO2 emissions, which are going to add to the stock of CO2 in the atmosphere, which in turn is going to affect global temperatures. So that's the standard, what people sometimes call the carbon cycle in the model. And then those global temperatures are then in turn going to result in changes in local temperatures, and these changes in local temperatures then are going to affect the economic conditions in each location. And in particular, they're going to affect the productivities or the productivity of firms in a particular location. So on top of the purposeful innovation that firms do in that location, on top of that, there's going to be an effect from local climate. And they are also going to affect the amenities, how nice are these places to live in, and therefore, you know, how attractive they are for others to come in and live there. So they're going to affect the amenities, and they're going to also affect fertility and mortality rates, and the difference between the two I'm going to call natality rate. So that's also something that we're going to incorporate in this model. Okay, and so once we bring all this in, we have a model in which, you know, the economy is evolving, is using energy. Part of that energy is fossil fuels that generates increases in temperature, which in turn feed back into the characteristics of these local economies, both through productivities and through amenities. And so that gives us kind of all the main kind of components of a climate model. And so then what we're going to do is we're going to take this model and we're going to quantify it at the 1 degree by 1 degree level. So this is 1 degree latitude by 1 degree longitude. And so we have data for our baseline year is going to be 2000. We have the data for population and income in each one of these squares. In 2000, we're going to make the model in the period 2000 exactly match that, which is going to give us all the local productivities and the local amenities in the baseline year. And then and we're also gonna use data on mobility, so how people change locations over time between 2000 and 2005. We use data 2005 and 2010, and then to match or to calculate what the frictions, mobility frictions are between locations. And then we're also going to use trade data or some of the estimates of the gravity equation, which tells us how costly it is to move goods across space. And so in some sense, it's kind of state of the art, we think, in those dimensions, and it's kind of fitting all the data on the flows, on these flows that we have in these baseline years. And we're going to allow this natality rate, the birth minus the mortality rate, also to depend on income and temperature. And of course, where people are born matters because it's costly for them to move. And that's also going to be affected in principle by temperature. Okay, so then there's three key components that have to go into the model in order to at least to think about the climate aspect of the model. So the first one is this local temperature downscaling. So what does that mean? It means how does aggregate temperature or world temperature translate into local temperatures? And this is kind of part of the heterogeneity, spatial heterogeneity that I was talking about before. So what this map here shows you is the scalar that we're going to be using, and that we're estimating using, you know, all sorts of local characteristics. And it kind of matches well with some of the IPCC numbers, etc. So what this map is telling you is, if there's a 1 degree increase in global temperatures, what's the effect on local temperatures across the different locations? And you can also see kind of the resolution that I was talking about. The 1 degree by 1 degree is 1 degree by 1 degree is each one of these squares. We don't have all the world. There's some countries that we don't have, like Libya or parts of Greenland, etc. But you can see that we have most of the world. And so you see that 1 degree increase in global temperature actually means a much larger increase in some parts of Siberia, Alaska, northern Canada, but it actually means much less of a 1 degree increase in other places like Australia and South America. So the effect of a 1 degree global increase is not the same across space. Of course, South America and Australia are already warmer than some of these other areas. And so what that also means is that, you know, that half a degree increase may actually make more damage there. And that's what we're going to end up finding in a second.
Esteban, is this a deterministic function, or is it probabilistic? Probably one doesn't know exactly how to downscale it.
So this one we're going to take as deterministic in the sense, and not only deterministic, we're going to make it even stricter. We're going to make it also fixed, right? Now, of course, what we may have a lot of uncertainty about is the evolution of global temperature. And so that of course may vary, and we can have different scenarios for that, etc. But how that then, you know, maps down or downscales into local temperatures, that's the part that we're keeping fixed, because we're making it, you know, a function of some of the characteristics of that location in terms of, you know, its location, elevation, distance to coast, albedo, that type of thing. Okay, so that's the first component. The second component is the damage functions, and Markus mentioned this before. So how do we think about what's the effect of an increase in local temperature on both amenities, how nice it is to live in a particular place, and productivity in a particular location as well? And so here's what we're going to do in order to try to estimate these functions. First of all, we're going to take the model and we're going to invert the model for a number of years. So 1990, 95, 2000, 2005. And so what does that mean? It means we're going to take data at this 1 degree by 1 degree resolution. We're going to recover the amenities and productivities implied by the model so that the model can exactly rationalize that data. And then, you know, then now we have the amenities and productivities, and we can use that to estimate these damage functions. So namely, how costly it is in terms of amenities or productivity to have higher temperatures. And so these are the functions that we're estimating. So namely, take the amenity one, as log amenities in a particular location at a particular point in time are going to depend on temperatures in that location, but they're going to depend differentially depending on what's the temperature of that location. So we're going to allow for the effect of changes in temperature to be different for locations that have different temperatures. And then we're of course adding you know, location fixed effects and some, you know, region time fixed effects and things like that. And so we're going to run it for amenities, we're going to run it for productivities, and you can see in the graphs below the result of this. And what is this telling you? It's telling you, look, if you're in some of the coldest places in the world, a 1 degree increase in temperature, a 1 degree Celsius increase in January temperature in those locations are going to increase amenities by 2.5%. So that's what this number tells you, right? And so as you go to warmer and warmer places, eventually you cross zero, and then you get negative numbers, which means if you're in some of the hottest places in the world, a 1 degree increase in temperature actually decreases your amenities, right? And so if climate change is something bad, you're gonna have that, well, temperatures are going up here and you're losing amenities as a result of that. And you see the same for productivities. Actually, the numbers are a little bit larger the numbers that we get for productivities are a little bit larger. So the number here is 10% rather than 2.5%. And you can, you know, again, like an optimal temperature here where you go from positive numbers to negative numbers. So these are the damage functions that we're gonna get. But notice one thing, there's a lot of uncertainty here. So that's, again, going back to one of the points that Markus was making. You know, yes, we have some estimate of this. Yes, we have some significant effects for low temperatures and for high temperatures, but there's certainly a lot of uncertainty about these damage functions and where they are. And partly is because, you know, the effects so far, I mean, as we said, like these effects are very protracted. We've seen some effects of temperature, but, you know, we need like a longer time series of this in order to estimate these effects more precisely. And so a lot of the uncertainty in these estimates are going to come from the uncertainty in these damage functions. And so this is something to keep in mind. This is actually something very important. Yeah.
So there's some clarification questions. Some people would like to know what R is and S. I think R is region, I guess.
Oh, sorry. R here is the region. So think about this 1 degree by 1 degree square, right? T is time, and then S is groups of this region. So we wanted to add some kind of fixed kind of dynamic effects here, so or trends, you know, or control for some trends. Of course, we cannot do that at the square level because that's our variable, kind of our dependent variable, but we can aggregate a little bit and add those trends for those kind of more aggregated regions. And so that's just a way to control for some of the trends, differential trends that you may have across regions and not attribute that to climate.
The two more questions I would like to ask. One is, so Robert Owen would like to whether you can allow something, let me call it a Gulf Stream effect. So let's suppose the Gulf Stream is drying up and suddenly Europe is much colder. Can you incorporate this in your analysis as well? And the second thing is,
we could, and the way to do that, I think, would be to change that scalar that we were talking about before. So how do you go from global temperatures to local temperatures? If you think that scalar may change exactly because you have a change in which, you know, particular regions are differentially now affected by those global temperatures. So that would be the way to do it. We can, I mean, there's no difficulty in doing as long as you have good estimates of those scalars. Now, of course, you know, there's very sophisticated models of that out there. The key is, you know, at the end of the day, we need something that we can combine with our quote unquote sophisticated economic model and put it all together, right? And so we need to somehow simplify the climate model, because otherwise those models can be very, very large models to run. And so that's why we haven't incorporated this. Now, of course, particular phenomenon like the one you're talking about, we could incorporate.
Then the other question is, when you talk about these damage functions being uncertain, for what horizon is it? Is it like, if I look 20 years out, 30 years, how does the uncertainty evolve? Is there some mean reversion or not? Or is it non-mean reverting, or what do you assume for that?
I mean, so this is what we're estimating, and we're estimating it over this 20-year period. Why this 20-year period? Because we have the data at the local level for this period, and we think it's a period in which we're starting to see some of these effects of climate, and so we have a chance of estimating this. Now we're estimating these functions like I said, like heterogeneous effects by temperature, right? And so again, as the world changes, of course, places are going to be in different points in this curve, and so the effect that they're going to experience is going to be different. So that's the extent to which we're capturing that. But we're not capturing more than that, in the sense that, of course, one can think that these functions themselves are not stable over time, but that, I mean, I would say if we're having trouble estimating this, estimating how these functions change over time, we can there's definitely no data right now that can be used in order to estimate that. So that's like something that we just still don't know. Okay, so the other part that is kind of important here is the following, and this is going to play a key role when we talk about carbon taxes. So how do we think about fossil and clean energy cost or the price of them? And one key aspect of this is to think about how costly is it to extract the carbon that is out there in the world, right? And so, and part of this is, well, you know, the more carbon you extract, and that I'm going to measure as like the cumulative emissions of using that carbon, if you will, the more carbon you extract, the more costly is it to extract the carbon, okay? And so, you know, as carbon, I mean, if we use more and more and more of it, we're going to be kind of, it becomes more and more expensive to extract. And that, of course, you know, makes us use less of it and substitute towards clean energy. And so, you know, eventually there's no carbon. And so eventually, you know, we use it all. And if we use it all, then of course, the only thing that we can use is clean energy. And so how does that, and so we're going to assume this, or we're going to match this function of the extraction cost of carbon using some of the evidence out there. And it's going to asymptote, of course, at the maximum carbon reserves of the world, which are what I think 19,500 gigaton. That's I think that's what we assume in this case. And then, you know, so this function is going to be crucial. And then we're going to match the actual productivities in fossil and clean energy so as to match use today at the different kind of, we can do that at the country level. And then we have the trends in that use. And so we're going to match the fossil and clean technology growth to match those trends. So we're going to quantify them to match those trends. But this function, I'll come back to this function because this function is going to be important. Okay, so that's kind of the setup in some sense, in a very, very brief description of it. And now let me show you some of the results. So I'm going to start with the baseline scenario. And so the first thing that I'm showing you here is CO2 emissions on the left, and then global temperatures on the right. And so the blue line, or the CN line, is the model that I was just describing, or the quantification that I was just describing. The dashed line is the IPCC scenario that they classify the different scenarios according to what they call RCP. And so this is RCP 8.5, which is kind of like an extreme scenario for that. So this is kind of a case that is pretty, you know, where climate actually is very, we don't do anything about it, and everything kind of goes bad, and climate actually gets pretty bad. So that's the situation that our model is kind of replicating, and it's replicating kind of fairly closely. And then you see that, you know, carbon emissions grow. At some point, they start declining. Why do they start declining? Because we start using the carbon, and the cost of carbon starts increasing. Like that's that curve that we just discussed. Now, in general, like all the scenarios of the IPCC actually have this. You see that they have this kink here, and then it comes down. They just have an abatement technology that comes in and says, well, you know, solves the problem, if you will. we have it endogenously through that function f. And that leads to temperature increases, you know, of, in this case of, you know, all the way up to about 7 degrees Celsius, global temperatures increases of that, you know, again, match fairly well with what you see in that scenario. Okay, this is...
Esteban, let me just interject again, sorry.
Yes.
Because some people have the view that, I mean, I guess that most scientists think there's often a no point, we are actually past the point of no return, so we can't return anymore. In your model, you return it at least after 100 years or something like that. That's also what the IPC is essentially saying.
Well, I mean, depends on what you mean by return. I mean, you have to return in terms of emissions simply because you use it all. Okay. You may not return in terms of temperature, in the sense that, well, you go up, and then as you see, I mean, yes, it comes down a little bit, temperatures come down a little bit, but not that much, in fact. I mean, temperatures stay up because, you know, seas absorb, I mean, there's a whole, you know, science of what happens to that carbon after it's emitted, and some of it is absorbed, but that process is very slow. And so you can see how once you get up there, you know, temperature declines very slowly.
But the agents in your model that take this path as given for certain, or is it? Are there...
No. So this is the result of the actions of these agents given current incentives, right? I mean, now and then we're gonna make them do stuff by changing the economy and changing the policies in the economy, and of course that's gonna change all of this.
No, I understand, but is there some risk around it? What probability do they assign to this scenario? Is it an equilibrium path? I think that's the equilibrium path. If they don't,
that's the equilibrium path, and that's the equilibrium path that they see. Now, yes, let me leave it at that. Okay, so this is what are the effects of this path that I just showed you on both the amenities in the different locations and the productivities in the different locations. And so you can see that, you know, amenities in northern Canada, Siberia, etc., they grow, or according to this, they're going to be much better, about 20% better in those regions. US and Europe are going to be about the same. And then, of course, South America, Africa, and Australia suffer. They don't suffer too much in terms of amenities. They suffer about 10% in terms of amenities. Productivity is a little bit more extreme, much higher productivities in these areas. Against the US and Europe, you know, varies a little bit depending on where, but they are, you know, they lose a little bit in certain areas, gain a little bit in others. But again, this area of Africa, South America, India, they lose quite a bit in terms of productivities according to this. And this is, I should have said this is all in terms of those damage functions, this is always the baseline case. So this is the actual, you know, point estimates of it. We can, of course, use the whole distribution of outcomes, and I'll show you what that distribution gives you in a second.
Esteban, some people would like to know what is the definition of an amenity, how to measure it. Can you give a quick summary?
Cool, of course. So in this model, the amenity is when you go to a particular place, and it's a utility shifter for you. So how much do you like living in that particular place relative to some other place? And the way we estimate it, or the way we quantify it, is what does it need to be in order for the model to be able to rationalize the number of people that live there, conditional on the income of that place, and which also leads to the productivity of that place. So you can think about it as a system where we know in the data how many people live in each location and the income in each location, and we can invert that system to obtain those amenities and those productivities. Okay, so that's kind of a simplified, slightly simplified, but that's kind of gives you the logic of how we're getting it, how we're measuring it. So
you back it out from migration pattern, essentially.
From population counts, from migration patterns, from the changes in population, we're getting the migration cost.
Okay.
Okay. Okay, so of course this temperature change leads also to these changes in fertility, etc. That actually turns out to be pretty small. So about, you know, the difference with or without climate change or global warming, it's about 30 million people less with warming, but you know, in relation to the total population in the world, is pretty small. And then, you know, but population in the baseline scenario will move because of the increase in climate into these more northern latitudes, in particular to those places that we discussed before, so Siberia and Alaska, and northern Canada, etc. And a little bit towards, you know, the northern part of the U.S. and some of the Scandinavian countries, etc. So that's what the model tells you. Of course, and here you can see the magnitudes that we're talking about for 2200. So which are, you know, 20-30% more population in these areas relative to a scenario where we didn't have increases in climate. Okay, so that's the baseline scenario. And then, so what's the implications for welfare? You can see here the welfare changes of a person that is in these different places in 2000. What's the effect of living in a world in which there will be climate change relative to living in a world in which there is not climate change, taking into account that they can adapt in all these ways that we've described, by moving, with trade, by trading, etc. And again, and so again, you have all these southern regions that are going to lose significantly, while some of the kind of intermediate regions, in particular some of the richest places in the world, are not going to be that affected, or at least according to these calculations. And then there's the big winners kind of in the northern part. And so you can see it here. This is the distribution of outcomes, population weighted. There's a big group of losers here that are going to lose about 8% of the kind of present discounted value, if you will, of their welfare, while there's a group here that are going to be essentially indifferent. And then there's like a tiny tail there that are going to, according to this, be better off, which is these red areas over there. And this again is for the baseline scenario. If you go to the worst case scenario, of course, you're shifting the distribution to the left. So we've talked a lot about risk and kind of uncertainty about these outcomes. There's huge uncertainty about these outcomes. And so you can see it here for real GDP and welfare over time. So the case I've been talking about are the solid lines, and here you see the different intervals, and you see that those are huge. And so these intervals just come from these loss functions and kind of the uncertainty in those loss functions. So we know really very little about the evolution of these losses in welfare and real GDP in the aggregate. These are incredibly uncertain according to this. We know much more though about the distribution of these losses, because in all these scenarios, the distribution of these losses is kind of similar. So that's what this graph is supposed to represent. So what I have here is the low 95%, the baseline that we've been talking about, and the high 95% of those damage functions. And you see how, you know, the distributions, you know, change a little bit, but they don't change that much. They're just shifting around. So the big uncertainty is reflected in that other graph over time. And so huge uncertainty about the level of the effects for the world, not so much uncertainty about the fact of who are going to be the big losers of this and who are not affected or potentially win a little bit. Now I've talked a lot about adaptation mechanisms. So this shows you, you know, what is the effect of migration cost on the cost of climate. So this is the benchmark case relative, or a diff and diff, of the cost of climate in the benchmark case relative to a case in which migration costs are 50% higher. And so what the red areas, again, are the areas that win in the current scenario relative to a world in which it's costly to migrate. So they, in some sense, Siberia doesn't want a world in which it's costly to migrate. They benefit from migration, while Australia actually cares a lot about migration being cheap, because a lot of their agents eventually are going to kind of migrate out, and that's kind of an important adaptation mechanism for that. And so migration is huge in terms of it can really double. I mean, like if you increase migration cost by 50%, the cost of climate almost double. You can see it. You can see it here. Now, there's a phenomenon here, of course, that is that if you lower migration cost, yes, you allow people to adapt to this. But if you lower migration costs, the world economy also expands. It's growing, enhancing for the world economy, and that in turn uses more energy, which makes climate change worse. And so that's kind of one of the mechanisms that Markus also was talking about. We have to be careful with these policies. We want these policies, but if these policies are also, you know, increasing production a lot, then they use a lot more energy, and that can kind of end up actually harming the environment. And so you can see that in this dashed line. So this dashed line is when we incorporate that effect, then the effect of the higher temperature, the migration adaptation is a little bit lower. Okay, we can also do the same for trade. Those effects, at least in this model here, are very small. So trade doesn't seem to be like a huge adaptation mechanism. It is a little bit at the end here of the number of years that I have, but of the period that I have, but it's not that large. And then you can think about innovation. So of course it's important, like for the economy to, if we're going to move to Siberia or northern Canada, right? There's not that much production there. It's not that productive to be there. And so an important part of this is, well, can we go to there and innovate so that, you know, in the future, after perhaps some time, the area becomes better, right? And so this is telling you what's the effect of higher innovation costs on the effect of climate. And so, of course, if costs are higher, then these areas or these areas are better off in the baseline than in a situation in which costs are higher than while Africa and South America, again, lose a lot from higher cost of innovation. But perhaps, you know, surprisingly is if you lower the cost of innovation, that is actually, again, bad for climate. And part of it is that if you lower the cost of innovation, then more people go to areas, go to India, go to China. Those places flourish more. As a result of them flourishing more, then climate comes, or climate temperatures increase. And when temperatures increase, those areas are hit and suffer from it. And so in some sense, the economy goes into this equilibrium in which it puts more activity in areas that are worse affected by climate in the future. And so that's kind of a tricky aspect of changes in innovation. Yes, they help, but they also move economic activity into some areas that are not.
Can you say a little bit more about this innovation
in the future? Yeah.
I will give you extra time at the end. There's local innovation? Is it the innovation process? If I'm surrounded by a lot of innovators, I will also be a better innovator?
So the way it works in the model is it's all about market size. Mm-hmm. So if you're in an area, so if you're in New York, your market is very large, and because your technology, you can produce for everyone. Once you innovate, you produce for everyone. That gives you incentives to innovate. And so, you know, if you can trade with more places, if you live in an area that has more purchasing power, that all enhances innovation. And so as people move to Siberia, say, you know, at the beginning, it's not very productive, but once the market there develops, there's going to be more innovation, and there's going to be an endogenous process there. And if you facilitate that process, that helps, you know, moving to Siberia, and so developing the cities of the future in Siberia, as you were talking about before. And so in the model that can happen, and how easy it is to do that or not depends on this cost of innovation.
But these innovations are all climate innovations or any type of innovation?
Oh no, this is just, it's not climate innovation, it's general production innovation. It's not climate innovation, that's important. Now, the way climate innovation, depends on what you mean by that, I guess, but I mean, one way in which it affects climate innovation is because the general level of technology in one particular location is also affecting the technology to use fossil fuels and clean energy. And it actually affects the technology to use clean energy a little bit more. So if an area is very innovative, it's also going to innovate on fracking, but it's also going to innovate on clean technology. And the way we're parameterizing this in order to fit those growth in those technologies, as I mentioned before, is that it's going to affect actually clean technology a little bit more. Okay, so let me, I mean, I don't have a lot of time, but I want to mention or talk a little bit about policies, and in particular carbon taxes. So obviously, you know, in the poll, everyone likes carbon taxes. This is kind of the main policy that is in general advocated by economists, and you know, it makes sense. So let's bring in carbon taxes. Let's put a carbon tax. What I'm going to do is I'm going to impose a carbon tax everywhere in the world, so to all locations, and it's going to be locally financed. And so when you see here is the CN was like our baseline case, the one I showed you before, and then I have 3 other cases of taxes of 50%, 100%, 200% on carbon, and kind of the evolution as a result of those taxes. And so just for you to get an idea, 50% would be like the EU emissions trading scheme, kind of the max that it has reached. You know, 200% would be similar to what the Swedish tax today. So just for you to kind of fix the ideas in that sense, and look at what happens as a result of the tax. So obviously the tax reduces at the beginning, it reduces carbon use or carbon emissions. And then over time, what it does essentially, it kind of delays the use, right? It shifts the curve to the right. And so what does that do in terms of temperatures? Well, it lowers temperatures, right? So the increase in temperature is lower, but then eventually it catches up. And so why does it catch up? Because eventually, you know, you don't use the carbon at the beginning. Because you don't use the carbon at the beginning, the cost of extracting carbon don't grow as much, right? And as a result of the cost of carbon not growing as much, right, then in the future you use a bit more carbon, right? So eventually you kind of use the carbon because what is very dominant in terms of the evolution of the cost is the fact that, you know, if you haven't used the carbon, getting the carbon is actually fairly cheap in the future. And so in some sense, to use like a common phrase these days with the COVID crisis, is you're flattening the curve, right? So what you're doing is you're kind of flattening, in some sense, the temperature curve with the tax, right? By, you know, spreading its use over time. You're making people use it later on. And so what does that do? If you look at over time, well, it has some significant cost today, but of course it increases or lowers temperature increases, which in turn, you know, make the economy perform better in the future. And so there's some growth effects and some larger GDP and overall welfare, which is what I have on the right, in the future. And so, you know, again, as we know from all of this, it depends on, there's cost today, there's benefits in the future, and it's all about, you know, weighting those things, and it's all about what is the discount factor that we use in order to do that. And so Markus was talking about, well, the importance of discount factors and the fact that, you know, if there's risk, we may even want to incorporate that into our discount factor when we look at the future. And so here on top of that, there's growth. And so we in some sense, how much we can play with the discount factor is also limited by the fact that, you know, there's growth, and we don't want these calculations or PDV calculations from today to explode. And so, you know, so these carbon taxes have a role to play, have some benefits. They're not huge, or how big they are, I guess, depends on these costs today versus these benefits tomorrow, and how you evaluate those relatively. They, of course, help you know, the areas that are more affected in the world. And so there's a big, you know, disagreement in some sense of who wants them and who doesn't want them. And the areas that definitely want them are, you know, Africa, South America, India, and China. The ones that don't benefit so much is the rest of the world, and in particular the northern areas. Now, you know, keep this analogy of flattening the curve. Now, of course, flattening the curve, the same as what we know with the COVID crisis, you know, flattening helps a lot if the vaccine comes, right? If the vaccine comes, then, you know, it's great to delay things, because eventually we don't care about, you know, all those potential future cases, because there's a vaccine and anyone can take it. And the same kind of happens here if an abatement technology comes, right? So carbon taxes are very effective because they delay the CO2 consumption, they push it to the future, right? And that's great if eventually there's a technology, an abatement technology that, you know, eliminates the emissions or eliminates the cost of using that carbon. Right? And so if that comes, then of course delaying, if that's going to come in the future, then of course delaying is great. And so this is an example in which an abatement technology comes in year 2100, and it comes, and then, you know, emissions go to zero essentially. You can capture all that carbon, say, and then of course, flattening the curve is not only delaying, you are actually also reducing the total emissions significantly by using a carbon tax. And that actually leads to much larger gains from the carbon tax. You can see the cost today remain more or less the same, but the gains in the future increase substantially. And so in our calculations, if an abatement technology comes in 2100, you double the gains from the carbon tax itself. I mean, forget about the gains from the abatement technology, controlling from the gains of the abatement technology. The carbon tax itself has much larger or leads to much larger gains if in the future we're hoping or we think that an abatement technology is going to come. So this idea that the carbon tax is the key policy, yes, it's a good policy, but it's a particularly good policy. It's really, when it becomes a really good policy is if we're hoping for an abatement technology. So a little bit similar to like I said, to these COVID issues. So Markus, should I stop?
Or you can have another 2 slides to finish your talk.
Okay, so final thing is clean energy subsidies. We also try clean energy subsidies. They don't have a big effect on temperature in general and on emissions. The reason is simple, is they lead to more economic activity, more energy use in general, because they lower the cost of energy. And so what that does is the composition of clean to fossil changes, of course, but overall you increase the use of energy, and so that's not so good for the climate in general. Has very small effects on temperature. In our calculations, it does have an effect on the economy. It's a good effect on the economy, and it's particularly good for the regions that are most affected, it actually also helps places like Scandinavia, where there's, you know, where people use a lot of clean energy, and because of that, the clean subsidy in some sense has a big effect on reducing the cost of energy. But again, and it also helps other regions. Like we were, for example, interested in Paraguay here, that looks very red in the map, and the reason is, well, that they actually use a lot of clean energy because they have because of their geography, because they can use kind of.
So Esteban, but if I do clean energies innovation subsidy, so this clean energy subsidies, do they lead to more innovation in clean technology as well, or is it just for the use of clean energy?
This is for the use. So the one that we're using is for the use. You could also incentivize innovation in clean technology itself, but that's not the policy that we have. This is a policy to use. So you're subsidizing clean energy. That's what it is. And that policy on its own, it can be growth enhancing, because at the end of the day, you're subsidizing an input, and you're subsidizing it in places that where subsidizing production may be good, but it's not as a climate, as a way to fight against climate change. At least in these calculations, it doesn't seem super effective. Okay, so let me conclude. I showed you, so there is an agenda here, which is trying to think about models of climate. I think economists have a lot to say here in bringing models of climate that include these micro foundations and adaptation mechanisms that, you know, we've used for all sorts of phenomena. It's kind of our bread and butter, if you will, but we haven't really used that much for climate. I think we have a lot of tools to do this, and this is like, because it's such a protracted phenomenon, because it's so global, this is really kind of a case in which, you know, using models and using the type of micro foundations that have been advocated in other areas is particularly important and effective. It's very hard to extrapolate from, you know, local estimations that are purely empirical. We find very large role for adaptation, particularly adaptation through migration, and we also find that carbon taxes can be good, but particularly if we're hoping for future abatement technology. On their own, they tend to just flatten the curve and delay the consumption of carbon to the future. Thank you.
Thanks a lot, Esteban. Fascinating talk. I really like this flattening the curve. And, you know, there's this talk about this green paradox in environmental economics a lot. And that's in the cross section across countries. You know, if one country does a lot for the environment, it reduces, you know, oil prices and all that, which makes it cheaper for the others to use it. Here it's over time. It's essentially a similar thing over time, but it has this abatement technology, which, you know, is an over time phenomenon. So doesn't the conclusion of your model, doesn't it mean we really have to invest in innovation to get this abatement technology, not only in 2100, but already 50 years earlier?
Exactly. So I mean, I think it's both, right? I mean, so there's been a lot of energy, and sometimes it's portrayed like this carbon tax is portrayed as the one solution, right? And the solution that is gonna, you know, solve the problem. If we were just like politically savvy enough in order to make it happen, then everything is gonna be solved. And what this is telling you is, you know, by all means do the carbon tax, but investing in abatement technology and trying to come up with abatement technology is crucial, because otherwise you have this effect of delaying things to the future. And a key part of it is that, you know, at the end of the day, the elasticity of substitution between energy and fossil fuels, right, is not that large, right? I mean, at least everything that we estimate, I mean, they're totally not infinity, right? And so what that means is that we still, or the economy still uses carbon, right? And still will use carbon. And so the question is, you know, and so carbon taxes, even if they are high, we're going to reduce our use, but again, less, a lot today, but less in the future.
Okay, like we're investing in vaccines, we should invest in abatement technologies. Your analogy holds very nicely. So there's some questions I would like to throw at you, more from the urban agglomeration literature side. So somebody asks about, so do you think after COVID, agglomeration effects for innovations are much less important, and do you have to recalibrate your model? So in your model, it's the case if you live in a big city, we innovate much more because we benefit from the agglomeration benefits. But now we have discovered all this Zoom technology and all these technologies. This whole model has to be recalibrated because local spillover effects are less important. Yeah. What's your take on this? It's a bigger question in a sense.
I know. I mean, I've been thinking a lot about that. I mean, I think it's an interesting question. Yeah, I mean, if this all continues, yes. I mean, so far, I mean, we're talking hundreds of years, not 6 months. This has been 6 months. But the question is whether this is going to have kind of more permanent effects on the distribution of economic activity in space. And if in fact it does, then I definitely think that we need to take that, and we need to take that into account. Now, there's a key component to this that it's also true amenities, right? And the fact that more people lead to amenities that kind of effect also on consumption is there. We've seen it in cities. And we've seen it as a kind of an agglomeration effect for cities as well. So, you know, there's a production side, there's a consumption side. Are we want to disperse both in terms of consumption and in terms of production? We need to think about that, and we particularly need to estimate that. But I agree that it's an open question right now. It potentially could have an impact. My guess is that it probably won't have a very long-lasting impact, but I may be wrong, of course.
So let me, so a lot of questions came up, and I have to, sorry, I can't address all of them, otherwise we will take too long. But the migration costs, you know, that's, you know, many people asked, in this particular Stephanie Kesselman wanted to know, you know, the national borders and all this, how do you take this into account? Is it realistic that people relocate and you can really solve it through migration? And I mentioned earlier, you know, Canada might be more open, Russia might be not. So how do you deal with this in the model? And is it really migration? Is it a mitigating factor as large as you think, given that it's huge migration costs?
So let me first tell you kind of the narrow way in which the model kind of applies, and let me take then a kind of a little bit of a broader perspective. In the model, the way it works is I see people moving over a 5 or a 10-year period, and then, you know, I see what the prediction of the model is in terms of how many people should have moved during that period, right? Mm-hmm. And then I adjust the moving cost so that the model fits that movement exactly, right? And so I'm not taking a stand of exactly what those costs are. Are they borders? Is it just that, you know, moving to Siberia is costly because, you know, there's no airports there, or not that many airports, or I need to take like a dot sled or something? Or is it that, I need to go and get a visa? We're not taking a stand on that. It's just whatever explains or not explains, accounts for the changes that we see. So that's the narrow perspective. Now, of course, you know, over those 10 years that we're doing this, maybe migration was not large enough to really create like more macro changes in the system that could change those migration costs. So I don't know, closing borders because enough is enough and we don't want to allow for more migrants and things like that. So I fully agree that we need to think about what is it that those type of macro changes can do in terms of changing those migration costs and making those migration costs more severe. Right now in the model, what you can do is say, well, these are the baseline migration costs. I can do scenarios with more larger or smaller migration costs and see kind of how that affects the cost or the cost of climate change in particular. And so that's, in some sense, one of the reasons to have the model is exactly that you can do that, right? But of course, we're not modeling like the political economy effects that are going to in turn affect migration costs, etc. I think that's very interesting, and I think it's likely to matter, but it's not something that we're capturing right now.
So typically, I have one quick question, and then I have the general question we have in every webinar in this series. One quick question from Michael Rauscher. He would like to know, given that the tax might be not so effective, a global cap and trade system, is this doing better, or it suffers from the same problem you outlined?
It's the same thing. I mean, right? I mean, it's like there's a bunch of issues among these systems in terms of what works best in terms of reallocating the cost and the kind of the distribution of the cost vis-a-vis benefits to different groups in the population, etc. So these schemes are different in that respect, and some may work better than others in that respect. But ultimately, for what we're doing here, because the tax is rebated lump sum locally, those play zero issue. I mean, you could be more sophisticated here. We haven't been. So in that sense, that plays no role here whatsoever. But what plays a role is the fact that just makes fossil fuels more expensive, right? And so just in that sense, it's kind of Pigouvian, and as a result of that, people use less carbon, etc. I mean, so and everything that I've been talking about happens, right? So the flattening of the curve, etc. One works exactly the same as the other.
So our policy is that we always end at a positive note in this webinar series. So I would like you to make, I mean, typically it's in context of COVID, but climate change is an equally big challenge. Can you give us a very positive outlook given the challenge we face?
I think the positive outlook is that, you know, we are very resilient, and firms and individuals are incredibly resilient. And the economy is incredibly resilient. And in my experience of doing this work, the more I have models in which people get to react to phenomena, the more they do, and then they build things in other places, and the economy develops in different ways, in ways that we may not really understand today so well. But there's a lot of ways in which humans adapt, and human ingenuity is incredible in this sense, and it has been incredible in this sense. And so, I think we shouldn't fall into, well, of course we should do something, and we should be proactive in order to try to prevent all these phenomena, but we shouldn't despair in the sense that adaptation and the human ways of dealing with these problems are very varied and very rich, and in general have succeeded in ameliorating a lot the cost of this type of phenomena.
Thanks a lot, Esteban, for having you. It was fantastic, and let's hope that people react rationally rather than panic to get this good adaptation. And I think we need this framework to think about these things and what are the various trade-offs, and pick the right policies at the end.
Great, thanks
Markus. Everybody for hanging out. I know we ran way over time. I apologize for that. It was my fault, but there were many questions, and sorry that I couldn't, pass on all the questions.
Okay.
I see you around, Esteban.
Yes, thanks so much for the invitation.